Hello students, how are you guys doing? As you come into 9th and 10th, electricity is a new topic that you encounter, and along with it, there are certain concepts which are not familiar to you, which you'll have to deal with. For example, you'll have to deal with electric potential, what is resistance, what is current, so on and so forth. So let's cover some of those topics today. So by now you must be knowing about charges, the fact that charges come in two flavors, positive and negative, and the fact that like charges repel each other and unlike charges attract each other. So the first concept that we'll have to cover is called the electric field. Okay, so let's discuss what we mean by an electric field. So for our discussion, let's take a charge, let's take a positive charge and put it in the center of discussion. So around this charge, there is a region of space where the impact of this charge is going to be felt. For example, if you take a magnet, around the magnet, if you get an iron piece, the iron piece will get attracted by the magnet, right? So similarly, around this charge also, there is a region of space around which its impact can be felt. How do we test this? Let's say we are getting a positive charge and we are keeping it close to this central charge. Then this positive charge is going to experience a force of repulsion and it will move away. Supposing you are getting another positive charge and you are putting it little farther away, it will also experience a force of repulsion, but this force of repulsion is a little weak. Okay, so like that, the region of space around this charge where its effect can be felt is what is called the electric field. Electric field is a vector quantity, so we depict the electric field by drawing lines around the charge. So if you take a positive charge and this line begins at the charge and points away from it, that is how we depict the direction of it. What about the strength? In the case of a stronger field, we simply draw more lines that start from the charge and away from it. In the case of a negative charge, the arrows are simply pointing inwards. But what about if we have a group of charges together? Then the electric field lines, when two positive charges or two negative charges or a positive and negative charge is shown here. So I hope you have by now understood what we mean by an electric field. Now let's discuss about electric potential or electrostatic potential, because we are dealing with stationary charges. So to understand this electric potential, let's consider once again a positive charge. Let's establish the electric field around it. And now let's take a particular point. Let's call it point A, and we'll try to understand what we mean by potential at A. Different points around the electric field will have different potentials. So if you take a test charge means it is a small tiny positive charge, and we are trying to move the charge from infinity, means away from the electric field, far away from the electric field, and slowly we will try to get it within the electric field. The moment the unit charge enters the electric field, it starts experiencing the repulsive force, because this unit charge we have taken is a unit positive charge. It starts experiencing electric field. Now we have to push it from outside within the electric field and bring it to the particular point A. So in order to get this electric charge, by applying the force to this point A, we will have to do some work. So we calculate how much work did we do. Okay, let it be W. So we now go ahead and define the potential at that point A as the work done in getting this unit charge from beyond the field to within the field to that point A. Work done per unit charge is what is called potential. So supposing we are taking a different point B, and this point B is a little further away from A. So the work done in getting the unit charge from infinity to this point B will be less. Therefore we say potential VB at the point B is less than potential VA. So if we take the potential difference, the difference in potential between A and B, that is the potential difference between the 2 points within the electric field. We must remember that charges within an electric field will always travel from higher potential to lower potential. So let's talk about current. What is current? Current is nothing but the rate of flow of charge. So if you have an area where there is high potential and you have another area where there is low potential, obviously the current will start, the charges will start flowing from high potential to low potential. How much charge is flowing in a given time? That is what is called current, rate of flow of charge. There are different kinds of material which allow different types of current to flow through them. For example, copper, we say has high electrical conductivity. Therefore, it allows a lot of charges to flow through it with minimum resistance. On the other hand, there are some material which resist the charge flowing through that. So, those materials which resist the flow of charge are called resistors. Now let's take a simple circuit comprising of a battery, few resistances and a switch through which you can close the circuit or open the circuit. Now let's consider 2 points at the end of the resistor, point A and point B. Now as the electrons are passing through the resistor, they will experience resistance. The material within the resistor is going to oppose the flow of current. So the electron has to expend some energy as it is flowing across the resistor. So this loss of kinetic energy that is possessed by the electrons is, while it is traveling through the resistor, is given away as heat. And if you want to measure the potential difference between point A and point B, we use a voltmeter. A voltmeter is connected in this way and the voltmeter is going to measure the potential difference between the points. Now let's discuss a little more about resistance. We said that resistance is the property of the material of the wire. Let's take two pieces of the wire, one which is short, the other one which is longer. As the electron is passing through the shorter wire, it encounters lesser resistance because less material is there for it to obstruct in its path. Whereas for the longer wire, it will experience more resistance. Therefore, we say that resistance offered by the material is directly proportional to the length of the wire. Now let's discuss about if the area of the cross section of the wire has got any bearing on this. If we take a wire which is having small area of cross section, then the electron finds it difficult to go through the cross section of the wire. Whereas if we take a thicker wire, the electron has more spaces through which to navigate. Therefore, we say if you have a larger cross-sectional area, the resistance offered by it is less, or resistance is inversely proportional to the cross-sectional area. To understand the impact of cross-sectional area, let's discuss about traffic going through a narrow lane. We see that the cars and the bikes cannot move fast because the lane is narrow. On the other hand, if we have a wider lane, a 4-lane highway, then the traffic can move much faster. So the width of the highway is correlated to the cross-sectional area. So combining these 2 points, we can say the resistance is directly proportional to the length divided by A, or R is proportional to L by A. We introduce a constant of proportionality called resistivity given by the symbol rho, and we say R is equal to rho L by A. Now let's take the example of a battery. Let's examine a battery. The battery has two ends. One end of the battery has a pip and the other end of a battery has a dimple. The pip end is said to be in a higher potential and the end that has a dimple is said to be in a lower potential. So let's construct a simple circuit with our battery and let's examine what do you mean by the direction of current. If you examine this, the electrons are flowing from the negative terminal towards the positive terminal. So the direction of flow of electrons is in this direction. Whereas we say current flow is from the positive terminal towards the negative terminal. So this is a convention. Even though the flow of electrons is from negative terminal to positive terminal, in electricity, we say current is flowing in the opposite direction from positive terminal to negative terminal. Now let's perform a small experiment. Let's have a simple circuit. Let's put a battery of 3 volts. We want to measure the current that is flowing in the circuit. For measuring the current, we use an instrument called the ammeter. The ammeter is connected in this way. Let's make a note of the current. If supposing I remove this battery and put a larger battery, let's say 6 volts battery, what do you think will happen to the current? Will the ammeter register higher reading or a lower reading? Logically, we know that the ammeter is going to register a higher reading. Likewise, if we perform another trial with the still higher battery, we will see that as the battery's voltage increases or as the potential difference of the battery increases, there is more current that is going to flow through the circuit. So we say the voltage is directly proportional to current, or current is directly proportional to the voltage. Point number 1. Now let's consider the second trial. In the second trial, we keep the battery the same and we will keep changing the resistance. So let's have resistance which is 10 ohms initially, measure the current and call the reading as reading 1, and remove the resistance and put a resistance of higher length. What do we think will happen? Logically, because the resistance is going to impede the flow of current, the second reading will be smaller than the first reading. And we can repeat it for a couple more readings and we will say that as the resistance in the circuit increases, the current is going to reduce. Or we can establish the relationship that current is inversely proportional to the resistance. Point number 2. We can combine both of this and say that I is directly proportional to V by R, or we can say V is equal to IR. This in fact is called the Ohm's law. To summarize, we covered a lot of points today. We discussed about electric field, electric potential, resistance, current and Ohm's law. I hope this has been useful to you. Thank you so much for watching. I'm going to follow this up with numericals on electricity. So stay subscribed, continue to like and share.